Hi everyone, we're going to be talking about optimization problems, and the strategy consists of 4 steps. And the first one, we talked about this in class, was to define the problem. So we have to determine what it is that's being optimized, and remember that optimization means either finding the maximum or the minimum. So the second step would be to gather the information. And a lot of times just making a picture of the situation helps tremendously, and writing down any formulas that you think you might need. The third step is to write the function that is to be optimized in terms of the variables, and then trying to write the formula in terms of one of the variables. And the last step is to solve the problem and determine the reasonable domain and a strategy for determining the maximum or minimum value of the function, and just making sure that you go back to the original question and see if the answer makes sense. So this comes directly from the Laying the Foundation Algebra 2 activity. And so let's go on to one of the questions, which is number 6. Our town elementary school wants to fence a rectangular playground for the students. The school can afford 300 feet of fencing material. The playground will be built adjacent to one of the sides of the building, so only 3 sides require fencing. This problem that we did in class, all 4 sides required fencing. And so in this case, we have that only 3 sides require fencing, and the 4th side will be the wall of the school. So we want to calculate the largest, or the maximum, the largest possible area of the playground, and state the dimensions that give this area. So the first step is to determine the quantity that is to be optimized, or in our case, maximized. So the quantity that is to be maximized here is the area of the playground. Okay, so I'm just going to write step 1. We want to calculate the largest possible area of, and what shape are we talking about? Rectangular playground. Okay, let's take a look at step 2. And step 2 is to make and label a sketch. Write down any formulas you think might be needed to solve the problem. So let's draw a picture. Okay, so here we have the building. This is the school building, and we are going to draw a rectangle, which is going to represent the playground, and we don't know what the dimensions are. And we do know that the school can afford 300 feet of fencing material, so we know that we have these 3 sides, which will be 300 feet. So that's not the perimeter. Okay, so these are 3 sides. If we had all 4 sides, that would be the perimeter. And we can write down some formulas here. So we know that if we call this the width, this is also the width, and this would be the length, and I'm just calling the side that's longer the length, L. So let's say W equals width of playground, and L is equal to the length of playground. So the question is, what formula can we write? So I'm going to give you a couple seconds to think about it, and then I'm going to try something different with EduCanon, where I'm going to ask you to actually submit what you think should be the formula, considering that we know that the school can only afford 300 feet. Okay, now that you've gotten a chance to think about it, let's see if you got what I'm going to think is the equation. So we have W plus L is equal to 300. In other words, 2W plus L is equal to 300. We also know that the other equation, I'll call this equation 1, is that length times width is equal to the area. And we don't know what that area is. Let's take a look at step 3. We want to write a formula for the function to be optimized in terms of the variables. Next, try to write the formula in terms of only one of the variables. Okay. Step 3. So what we want to do is calculate the largest possible area. So we're going to go ahead and write area equals length times width. Now we want to get it in terms of one of the variables. So we're going to have to write width or length in terms of the other. So it seems like it'd be easy to isolate the length here because it's by itself already. If you were to isolate width, you could subtract L from both sides, but then you'd have to divide by 2. So let's go ahead and rewrite this as L equals 300 minus 2W. So because L is equal to 300 minus 2W, I'm going to rewrite the area as 300 minus 2W times W. So that's our function that we want to maximize. Okay, step 4. Let's solve the problem. We're going to graph the function, determine the reasonable domain for the problem, and determine a strategy for determining the maximum or minimum value. So what I'm going to do is let you go ahead and enter in this function. Let's rewrite it again. And instead of writing it as A and W's, we can rewrite it as, well, let's keep it as A's and W's. And I'm going to go ahead and distribute 300W minus 2W squared. Now that we have the function, area equals 300 times width minus 2 times width squared, we're going to go ahead and graph the function, determine the reasonable domain for the problem, and determine the max and min value, so in this case a maximum of the function, and then calculate it. So let's go ahead and take a look at our calculator and plug in the equation. We've got y. This is a TI Inspire. I don't have an online TI-84, so it's very similar in functionality. So just go to your y equals and plug in 300x minus 2x squared and graph it. Now if you graph it and use a standard window, you'll get something which is just not very helpful. So we have to determine a reasonable domain. So let's go back to our problem. And let's just think about the situation here. So we know that the length times the width is going to equal the area. And we know that the 2 times the width plus the length has to equal 300. So a reasonable width for this rectangular playground could be, say, 100 plus 100 plus L. So why don't we go ahead and try 0 to 100. So if we do that, let's go to your window. And it's going to look a little different from my TI Inspire. Oops, hold on for a second. I want to go to Window Settings. Once you go to Window Setting, let's go ahead and start at 0 for the X-min. And let's go to X-max and let's just try 100. Y-min, we're just talking about positive values here. And the Y-max, if we had 100 as a width and 100 as a length, then the area would be 100 times 100, which would be 10,000. So let's put down 10,000 and let's see what we get. Okay, that's definitely more promising. We can see that the curve of the parabola as it's going up, so we see that we need to increase both the domain and the range. So let's go back to window and go and increase our x max to say, let's see, 250, and our y max to say 20,000. And do that on your calculator too. And here we have our parabola. Okay, so now we're going to find the vertex, which is going to be where the maximum is. So I'm going to go ahead and let you take a moment and find the coordinates of the vertex. And go ahead and submit it in the next couple seconds. So in order to find the vertex on a T-line spire, it's a little bit different, but it's the same idea. Hopefully you found the lower bound and the upper bound, and the maximum was at when the width is 75. So let's go back to our problem here, and we can go ahead and write down that the area is maximized when width is equal to 75. I forgot to see what the units were here. Are we talking about feet? Okay, so 75 feet. And the maximum area is, this is 1.13 times 10 to the 4th, and we can actually calculate that as well with our equation. Area equals 300 times 75 minus 2 times 75 squared. And let's just confirm that. So we have, when I calculate it here, okay, $300 times 75 minus 2 times 75 squared. So 300 times 75 minus 2 times 75 squared. There we go. And what do we get for the maximum area? 11,250. Huh. Is that what we got here for the graph? 11,250. Oh, they rounded. Okay, here they rounded to the nearest hundredths position, so, which is why it's good to check with the calculator. Not the graphing, but just the actual equation. So the equation here shows us that it is 11,250 feet squared. Okay, let's go back to our problem. We calculate the value, and we determine the dimensions. Oh, let's go ahead and find we found the width, so we need to find the length. So the length actually is 300 minus 2w. So the length is 300 minus 2w. So let's go ahead and plug in our width, which is 75, and we get 300 minus 150, which is 150 feet. So the dimensions are 150 by, let's do 150 feet by 75 feet, which is interesting because when we had the four sides that we could manipulate the lengths of to maximize the area, it ended up being a square. But when one of the sides is, we don't have to actually fence, and we are able to manipulate the length and width of just the 3 sides, it actually ends up being a rectangle where the length is twice the length of the width, the distance of the width. All right, let's take a look at number 7. Kristen needs to enclose a rectangular pen for her cows. She has only 800 feet of fencing, so she will use the 60-foot side of a barn as part of one side of the fence. Calculate their largest possible area of the pen and the dimensions that will produce this area. So really similar problem to number 6. And what do we need to determine? We want to calculate the largest possible area of the rectangular pen. And the dimensions. Very similar to the previous problem. Okay, step 2, let's draw a picture. Even though these problems are real similar, the difference is that she will use the 60-foot side of a barn as part of, I want to highlight that. She will use the 60-foot side of a barn as part of one side of the fence. Okay, so this is going to look like this picture here. Here's my barn. So one side of the fence is going to use part of the barn, but then we're going to have the rest of the pen here. So the barn is 60 feet from one end to the other. And we have the width here, and we have the length. But in this case, what are we going to write down for this part of the pen here? So I'll give you a couple seconds to submit that answer. So hopefully you saw that this was equal to the length minus 60. Now once we have this, we're going to go ahead and write down our first equation. And we have 800 feet of fencing. So we're going to cover up these 3 sides. 1, 2, 3, but also part of the 4th side. So go ahead and write down an equation that takes into account all that information. Okay, so hopefully you saw that we know that 800 is going to equal the width plus the length plus the width plus the length minus 60. Let's go ahead and simplify. We have 800 is equal to 2W plus 2L minus 60. Or if we add 60 to both sides, we get 860 equals 2W plus 2L. We can even simplify more by dividing by 2, and we get 430 is equal to W plus L. All right, step 3. Oh, I'm sorry. And then the other equation that we're going to need, the other formula, is of course area equals length times width. Okay, step 3. Let's remind ourselves what step 3 is. Write the function to be optimized in terms of the variable and write it as one of the variables. So we want to optimize or maximize the area, which is area equals length times width, and we would like to have the length or the width written in terms of the other. So it doesn't really matter in this case what you pick. So I'll just be consistent and I'll write length is equal to 430 minus W. Now let's rewrite this formula, and we have the length, which is 430 minus W times W. Okay. I'm going to go ahead and, again, give you a few seconds to work out. It may take you more than a few seconds. And what I'd like you to find is, where is the maximum? Okay, where is the maximum of this function? Okay, so we can go ahead and simplify our formula to be 430W minus W squared. And if you went to your calculator and graphed it, if you use the standard window, again, it was not very helpful. So hopefully you were able to change the window settings. So again, we're just talking about non-negative values. So you can always start off at 0 and 100. And let's go to the last time we had 0 to 20,000. You can see what that looks like, and that's not quite enough. We need a bigger domain and a bigger range. So from there, you just kind of continue manipulating your settings. Let's try 250, and the Y max, let's try 50,000. And that's pretty good, but we need a bigger domain. So let's go to Windows Settings, and let's go ahead and do 500. Okay, and here's our nice parabola. We're going to find our maximum. So you do your left bound, your lower bound, and your upper bound, and you got 215. So we have width is 215 feet at maximum area. Okay. Now, go ahead and, at this point, calculate the length and what the actual maximum area is. Okay, in order to calculate the length, we're going to just plug it into this equation right here. So we have length equals 430 minus 215. And that gives us 215. Oh, okay. Is that right? Yeah. So we have a square, it looks like. And now we're going to calculate the maximum area. And so the maximum area, let's just make sure we know that the area here is going to be length times width. And that's 215 squared. And if we calculate 215 squared, oops, let's go home, calculate 215 squared, that's equal to 46,225. So let's see if that jives with what we got here. 46, that doesn't. Oh, yes, it does right here. 46,200, and then it rounded again to the nearest hundreds. So again, it was 46,225. 46,225 feet squared. All right, I hope that was helpful, and we will do number 8 during class together. So in your textbook, you have problems very similar to these optimization problems, and just let me know if you have any questions. Thanks. Bye.